We continue the principal component analysis with the second video. So we looked at the idea of that rotation-based analysis. So all classical multivariate techniques work based on this principle. And now let's take a look how we actually do this matrix rotation or rotation of coordinate system mathematically. So in the last video we established that in principal component analysis we want to rotate our data set so that my variance is maximized in my first and second principal components. So if this were PC1 and PC2, I now have my data arranged so that I see a lot of spread in this direction, but I also see a lot of spread in this direction, and then these principal components represent different variables. But how do I get my data set rotated into position? So how do we rotate a coordinate system? And it's done with trigonometry. So if I were to, let's use a simple 2D example. If we had an x and a y coordinate and we wanted to rotate this around the z-axis that basically sticks out toward me, so do a left rotation here by angle alpha, then my new coordinate system, if I shift this down, if I normalize my data around a 0 value and put that here, so this axis here, that x1, that would now represent both the original x and y variable. So that would be my x dash, and then I'm free to rotate the data set around the principal component 1 so that more variance is explained by PC2. But let's just stick with the first rotation here. So I want to rotate my entire coordinate system so that my x-axis is located this way. And so you do this with trigonometry. Let's rotate just a single point, and for simplicity let's assume that that is 0.10. So my x value is 1, my y value is 0, so x would be 1, and this point here is my 0. So if I want to rotate by a particular angle, I'll do this with trigonometric functions, if you recall this. So my new coordinates for this point that I have, that's a hollow circle here, so where that would sit on my new coordinate system is in units of the original coordinate system, x1 dash and y1 dash. So that's sinus alpha and cosine of alpha, and you can put that in the calculator and see if that works. So if we say alpha is 30, then I would get new coordinates, for example 0.5 and 0.8 if we use an angle of 30. And we obviously don't want to do that for just one point, but for all of my points in the entire coordinate system. And that I can do very simply with matrix algebra. So if I have my original data table, let's call this one here .1. What I need now is a clever little rotation matrix. Let's call this Rm. I can create a new data table, .2, that is rotated according to the angle that I like. So that angle, or the sine and cosine values, they get entered into this rotation matrix. And in R, that's a simple command, so I just use my data table 1 as a matrix and multiply it with that rotation matrix, and out I get a new data table that represents my entire rotated coordinate system. So that's how principal component analysis works in principle, or all other rotation-based techniques. I can then, so once I've done one rotation, I can repeat this. So my data table 2 becomes my data table 1, and for my second principal component I can rotate around another axis using another rotation matrix to get my .3. And in the lab you'll find a little exercise that shows you can actually do this in Excel. And I just want to show you how that works in a really simple example, just for you to get a feel of the nuts and bolts behind those classical multivariate techniques. So I'll briefly show you here what we're trying to do in the lab for this little exercise. Is we basically have a three-dimensional coordinate system here, like we had in our box. I have x, y, z axes, And what I've done here is actually I just put the corners of a cube in here as 0 and 1. And so that actually sticks out in the third dimension. So I have 4 coordinates in the front, and then those have the 0 value, and then you can think of it either coming out to you or in the back. You have the same in the z-axis. So it's a cube. So that's our rotation matrix here. That changes a little bit if we change the angle. So let's put in an angle here, let's say 20 degree. And what that does, it is rotates my cube around this axis here. So I'm rotating around the z-axis that sticks out to me. So this gives me a new coordinate system here, and I can rotate that one again around the next axis, so around the x-axis. So this one was rotated around the z-axis that sticks out towards me, and now, so we've done this rotation. Now we want to do another rotation around that x-axis here, and let's do, I don't know, a 30-degree rotation here. Now you can see this cube in, let me get this out of the way, in 3 dimensions. I don't know, let's put 50 degrees. Maybe that's a little prettier. I don't know if you can see the outlines here. But so not only have we rotated that box around one axis, but also around another axis, and now you can see the 3D shape of that box. So if you connect the lines here, this would here be here one side, and this would be the other side. So that is how that in principle works, and you see you can even do this in Excel. Excel has some matrix algebra built in, and you can create these new data sets with very simple operations, and it's even simpler to do in R. And of course you don't have to do this, so principal component analysis is just a simple command that does these things behind the scene, but I wanted you to know what that does and how that works. So it's very simple. All these classic rotation techniques, they just look at coordinate system from a different angle. So these simple rotations that you did in Excel, that is what principal component analysis does for you. And of course the secret lies here in that rotation matrix, so you have to rotate it into the correct position, and figuring that out, that is obviously part of the algorithm that's behind the principal component analysis. So we're not going to get too deep into that. I just wanted to show you how this works in principle. But you can execute these things very simply. So if you have a data set like this, you basically just run your principal component analysis as on that table. And one important option here is whether you work with the correlation or covariance matrix. So what that specifies is whether you normalize your data or not. So if you set this as true, so use the correlation matrix, that means that your data is normalized. That means that each of your variables that is in your original data set is actually valued equally. So let's say this was a climatic data set, and you have temperature values that go from 5 degrees to 15 degrees, and you have precipitation values that go from 100 millimeter to 3000 millimeter. So if you wanted the precipitation variables to be considered 100 times more important as the temperature variable, which you probably don't, then you would set this as false. So if you want each of those variables, despite their magnitude, to be treated equally, in that case you want to normalize this data. So then work with that option being true. Now you might be in a different situation if you were to work with, let's say, species data, and you had some species that are really much more frequent than others. There may be good reasons why you want those species to actually influence your ordination more. So the frequent species might be more important in your analysis. In that case, you can set this to false, so then the scale of those original variables are kept. So otherwise everything is normalized, so all the variables will be expressed as units of standard deviations from a mean of 0. So that's an important decision if you run a principal component analysis, what units you're working with. And as a rule of thumb, if all your units are the same, so if all your variable units are species frequencies, then typically you will set this to false, so because the units may matter. If you have variables that vary different units, like climate variables in millimeter precipitation, degrees Celsius for temperature, so in that case you almost always want to normalize your data so that you set this one to true. That's actually the default if you don't specify it, but that's an important one to know that exists. So regardless what package you use or which function you use, there's a bunch of them. That is a parameter that you want to set. So you have to look in the documentation how to do that. And then if you want the rotated coordinate system with your principal components here, you can extract this from your output file. So this will give you a data set that you can use to make ordinations and plots. You can also look at summaries. We go over what this reports in the lab, and your loadings, those are the eigenvectors. So those are the vectors that point towards the importance of the variables that we covered before. And if you don't want to do a custom plot with that output data set here of your principal component scores, then you can also use the simple biplot function here. This will give you an automatic ordination of principal component 1 over principal component 2, or you could set it to 3 and 4 if you wanted to look at those principal components. So to round this off before I let you do some of the labs, let me just go over a couple more pieces of vocabulary. The eigenvalues, so this is a number that's related to the variance explained. The eigenvalues, so those are reported for each principal component, and you can think of them as the number of variables that are represented by that principal component. So all the eigenvalues add up to your number of variables. So if your first principal component has an eigenvalue of 4, so you can think of that as 4 variables combined. Although it doesn't quite work like this, it represents more variables partially. Anyway, the variance explained is simply calculated as the eigenvalues divided by the number of original variables that you have. If you have 4 original variables, you divide the eigenvalues by 4, and that gives you the variance explained for each component. So another important thing to keep in mind is that the principal component analysis per se does not reduce the number of variables. So if you start with 56 variables, you get 56 principal components. And the question is, how many do you need to look at? And what's helpful in this case is to do a little scree plot with your eigenvalues or with your variance explained. So you're just plotting for each of your principal components, either the eigenvalue or the variance explained, same thing. And usually this curve here has an inflection point, so it drops quite dramatically in the beginning. So usually your first component explains a lot of the variance or has a high eigenvalue, and then the subsequent ones get smaller and smaller. Eventually this curve flattens out. And in those cases, so you don't really need to look at component 3, 4, 5, and 6. So 1 and 2 would in this case be enough. They capture most of your variance. Maybe look at PC3 just to be sure that you don't miss anything. But if you have a scree plot that looks like this, that gives you a rough sense where you want to cut off. So you don't always get a scree plot like this. So sometimes if your original variables are not highly correlated, this can go down much more gradually. And in that case, you have to look at more components. So another rule of thumb, if you do the scree plot in units of eigenvalues, if your eigenvalues fall below 1, then that's also an indicator that you may not have to look at those variables. So these are just rule of thumbs. So the best way is to plot them out and see if you can actually interpret it. And so the second big part that you want to interpret are the eigenvectors, or they are also called component loadings. So you can get this out of your object like this, out $loading. So this reports the component loadings. This will create this little table here. Or if you do that biplot, those loadings are automatically added as vectors to your principal component plot. And just to demonstrate how these two things are connected, so the eigenvectors just like I showed them to you. Those are kind of the shadows of that original cube, right? If you remember that, of the axes, of the original axes. These are also the correlations with your original variables. So you can express them numerically. And the length of those vectors represents the strength of the correlation. Let's say these vectors here are representing my original units. So these are species frequencies for species 1, species 2, and species 3. So I can also plot these values here in the form of vectors on my principal component plots. And usually I do this just with the second scale. So I have a scale of loadings here. So this is my origin with 0. And so if I look at my first PC principal component loading 0.9 and 0.1, so the 0.9 would sit here and the 0.1 would sit there. So that is the tip of this arrow here. And then I can do the next one here, -5 and 0.4. So my first component here will be minus 0.5, and here it's going to be 0.4. So those are the coordinates for the tip of the second component and so on. So that's another way to express this. So sometimes you actually see these axes here in addition, but these are not always put on. And you're actually free to scale them in any way you like. If you need a little bit more space for your labels, then you can make the arrows shorter, or if the arrows are too short relative to the points, you can just scale the labels in any way you like. So this is how this all is connected. So the shadow of your original coordinate system, the length of those axes represent the correlation with the original variables, and you can report those and get them out of the PCA as either loadings or eigenvectors. So those are synonyms. And so those are both ways to report your eigenvectors. So these are obviously very important. You can either report them as a table or as vectors in the original plot. So this is a bit more space efficient, but sometimes if you have lots of variables, it might get too crowded, and then what you can do is put that into a separate table, and this will still make sense and is slightly easier to digest. It may in that case be a better representation. Or you can put some vectors here that you want to talk about, but report all the rest of the vectors in the form of this type of table. And this can have more principal components. So you can interpret those tables and vectors independently. So if I were to look at just this table here, I would say, okay, my principal component 1 primarily represents species 1, and to some degree is negatively correlated with 2, and my principal component 2 primarily represents species 3 and to some degree species 2. Or if I look at this one here, I know that all the points, all my plots that are sitting here to the right, they have high frequencies of species 1. Those that are down here have high frequencies of species 3, versus those plots up here, they will have low frequencies of species 3, and those over here will be rich in species 2, but won't have any of the species 1. So that's how you can interpret your point cloud. And if those are colored, let's say these are different treatments, that you have a grazing treatment A and a grazing treatment B, the grazing treatment 3, you could very quickly see what sort of impacts those treatments will have, or whether your treatments have no influence. So if your red treatment, grazing A, is scattered all over the place, then you know it doesn't really matter. That treatment has no effect on species frequencies. So it's a great visualization of complex data sets. So with this, you can get started on Lab 2. That's enough for now. There's actually quite a bit more to say about principal component analysis, or ordinations in general. So we'll continue this next week with more videos. But for now, you know enough to do the lab. So let's do some hands-on exercises. So this will be interesting. We'll work with some simple data sets, but we'll also do a rather complex analysis of a spatial climate data set, of a gridded data set. So something that you don't usually see in the context of principal component analysis, but you can do these things on spatial data. So just to give you some examples how widely this technique is applicable, work your way through Lab 2, and next week we'll discuss the results together. So I'll post a few more videos on those particular examples, and we'll do some more vocabulary and some more interesting things about the nuts and bolts of the rotation-based techniques.